Yeah, folks, welcome back to another week of KDD 2. So we are in the middle of lecture 2 on high-dimensional data, and we are within this lecture in the middle of chapter 5, clustering high-dimensional data. So we talked about the challenges specific to clustering. So revisiting a little bit the cursive dimensionality stuff we had here in section 2, and then we had a short overview on subspace clustering algorithms, which take the bottom-up approach in terms of they start typically with one-dimensional clusters and then try to combine, or features, and then try to combine those lower dimensional clusters or features in order to get higher dimensional subspace clusters. This is more the a priori style way to do it. Most of the methods rely on, in order to apply a priori, on a monotonicity criterion or cluster criterion, which is monotonic. And now we go the opposite way, so to say, with projected clustering, starting with full dimensional clusters or full dimensional space, and then try to find lower dimensional projections, typically in a best first way, or well, we will see right in a minute what are the procedures or the strategies to find the clusters and the subspaces. So yeah, the top-down subspace clustering or top-down subspace search is basically there are different approaches how to do that top-down, especially how to find the features that are relevant to some clusters. Yeah, and the first one is the so-called cluster-based search, where you try to learn the subspace of an entire cluster from the entire d-dimensional feature space by starting with the full dimensional clusters and then iteratively refine cluster memberships of points and subspaces of the cluster. So in other words, you try to remove features that are not relevant to the cluster in order to and of course you may lose also some cluster members or get new cluster members in that case. So that is the refinement step of the cluster memberships, but basically the most important part is to remove features in order to find that subspace where the cluster which you started off in the full dimensional case really is accommodated best, so to say. Yeah. So this is the clustering approach or cluster-based approach, meaning that you try to learn the subspace of an entire cluster. And the instance-based approach, on the other hand, is that you try to learn for each individual point that subspace in which this point can be cluster best, so to say. Yeah. So we call that the subspace preference, and you also try to learn that in the entire feature space. That's why it is top down. So you always start in the entire full dimensional d-dimensional feature space and try to find those projections, those subspaces where the cluster or the points can be accommodated best. Yeah. And here the subspace preference, as I told you, specifies the subspace or the projection in which this point somehow clusters best to some criteria. Yeah. And then in the instance-based approach, typically, because here you try to refine clusters, here you try to come up with subspace preferences for points, and you still have to cluster. And how you do the clustering here in the instance-based approach, well, then you typically merge those points having this the same or at least similar subspace preferences in order to find the final clusters. And then there is a third way to look for, in a top-down way, to look for the right feature spaces, for the right projections, and that is similar to the feature selection processes, which is just random search. So you try to learn the subspace preference of a cluster or a point from randomly sampled points. Yeah? You just take a random sample and then see, okay, in this direction they have a high spread, so this is not the relevant attribute. In this attribute and this feature, the variance of the points is very low, so this is an important feature for for the subspace cluster, for the cluster, because of course you're interested in low variance, meaning that the points are very similar in the particular feature. Yeah, so the key question is, how should we learn the subspace preference of a cluster or a point? Yeah, so in this case, okay, you do random search, but in the first two ideas, you try to learn the subspace preference of an instance or of an entire cluster. And how should you do that? Most of the approaches, especially those two here, not the random search, but those two here, they rely on a very specific assumption, which is also known by the term locality assumption, meaning that, well, the name is program, so it means that you try to learn from the local neighborhood in the entire d-dimensional feature space. Yeah? So the subspace preference of a point or of a subspace is learned from the local neighborhood in the entire full-dimensional subspace, full-dimensional feature space. Yeah, and that is the assumption that this is possible, which is a clear contradiction to the curse of dimensionality, obviously. Yeah, so but still, the subspace is usually learned from the local neighborhood of cluster representatives or points, meaning cluster members, in the entire feature space. Yeah, so for the cluster-based approach, the local neighborhood of each cluster representative is evaluated in the full space, in the full feature space, full dimensional feature space, in order to learn the subspace of the cluster, yeah, where this cluster is really accommodated. And as I said, that's obviously a contradiction to the cursive dimensionality, saying that in the full dimensional feature space we don't find anything. That's why we are doing subspace search and projected clustering, subspace clustering. But okay, that's how it is. Yeah, and the same holds true for instance-based clusters, for the instance-based approach, where the local neighborhood of each point is evaluated in the full dimensional space to learn the correct subspace preference for this point. Yeah. Only random search approaches usually do not have the locality assumption. Yeah, but usually they need a lot of sampling rounds in order to get a chance to really get the right subspace cluster. Yeah, so random searches, random search approaches usually are extremely inefficient, or they have to really do a lot of sampling rounds to really have a significant chance to grasp the right thing, to sample the right things. Yeah?